Grabando. Adelante.
Hello, everyone. Welcome to this new IAA seminar. Today we have with us Dr. Isaac Figuero, who will be talking us about the computational intelligence and the big data context. He's working at the University of Granada and the University of Nottingham. So Isaac received his master and PhD degrees in computer science from the University of Granada in 2009 and 2014, respectively. And he's currently enjoying a distinguished senior research fellowship at the University of Granada, taking a teaching break from his position as an associate professor of data science at the University of Nottingham. His work is mostly concerned with the research of novel methodologies for big data analytics, and he has published more than 90 international publications in the fields of big data, machine learning, and optimization. He's editor-in-chief of the section editor-in-chief of the Machine Learning and Knowledge Instruction Journal and associate editor of several other journals. He's currently leading a knowledge transfer partnership project funded by Innovative UK and Unilever that investigates interpretable machine learning models for sustainable business operations. So the floor is to you.
Thank you. Thank you very much, everyone. Thank you for joining me. Thank you, Francisco, Emilio, and Manuel for inviting me to be here. It's really a pleasure to be here. I really thought everybody would be like, sophisticated, but then I saw one of my lecturers when I was a student in computer science, so possibly they will understand everything I'm going to say. Anyway, so what I'm going to be talking about today is computational intelligence, mostly focused on big data, which is what I've been doing for the last 15 years. And that might sound a little bit alien to you, perhaps, or perhaps not, because it's very much computer science oriented. But what I'm going to try to do is to learn those concepts easily and nicely so you can follow me, and maybe you can, is something, you feel like, oh, this is interesting, maybe we can follow up and maybe have some future collaboration, which is the main goal of this talk. So having that in mind, what I wanted to do before starting talking about this, and it doesn't want to, obviously, because I need to click here, is to give you a bit of an overview of what I do in my research. What I've been focused in the last few years is on big data. I'm going to come back to what big data actually means, but basically I've been doing quite a lot on designing techniques to pre-process data, to make data smaller, to make it more meaningful before doing any machine learning with it. And to do so, I've been using different computational intelligence techniques. And those techniques normally range from things like fuzzy logic that you may have heard about or not. Yeah, a few people say yes, a few people say no idea what you're talking about. And I'm not going to discuss it in depth, but I will mention it. I've been doing some evolutionary algorithms for optimization and machine learning, and quite a bit on deep learning. And that's what I did, let's say, my PhD, but then I moved to Nottingham, and then in there, what they wanted me to do is more practical stuff. They wanted me to apply what I do in machine learning and data science to real problems. And I've been doing quite a few things on healthcare, energy, transportation, and hospitality. Two of the examples I've been working on is with E.ON, which is kind of the Iberdrola from the UK and Germany. So we've been doing quite a bit of machine learning to understand how consumers are using their energy and try to sell them more and better products, obviously. And now I'm currently making ice creams with Unilever. So they gave me that duty, and I'm really delighted. Every time I go and visit them, they give me a magnum. They're quite good, right? Anyway, this is what I've been doing for a while now, but where I'm heading and where I have started to do, I'm not going to be talking about it, by the way, it's all about sustainability, making processes, making manufacturing processes, and any processes like what we do with Unilever to make them more sustainable. And that comes from two different aspects, to make it more, spend less energy, but also with techniques that are green. We call it green AI, because what we try to do is machine learning that is consuming less energy when learning something from data. And also, I'm more interested now in the idea of general purpose AI, which it doesn't mean that it's going to be robots building themselves, killing us all. That's not actually the whole thing. It's more about machine learning techniques that will adapt and will make our life easier whenever we don't know enough about machine learning. So we have a problem, and we simply fit that data into the problem, and it will find a model that will probably suit better that kind of data. So this is basically my research interest. And if you have anything that you think it falls within that kind of category, just let me know after the talk. Yeah, we can chat about it. But what I'm going to be talking about today is for the first 2 hours only about big data. Is that all right? I was checking if you're listening to me, but obviously only a few. So I'm going to be talking to you about what big data actually is, what I mean by it, basically not what people think it is, how to deal with it, and that's going to be a bit more computer science oriented. And then after that, I wanted to showcase 2 case studies of PhD projects I've been working with. One of them is on citizen science for galaxy image classification. Why am I talking about that? I have no idea, but that's the closest thing I've been doing to you guys. And actually, it's not even my work, it's Manuel's work and his PhD, right? But I was supervising that when I was with him in Nottingham. And then if I have time, I will get to this hotspot identification that has nothing to do with you, but it might be useful to understand why summarizing data, reducing data might be useful in many cases, and why updating models in machine learning is really good. Okay, so what is big data? Does anyone know? It is a fancy term that has been around actually for 20 years, not for like 5 years ago. It's actually not fashionable anymore. If you talk about big data, people are like, that's from the past. We don't do that anymore. And many people call big data things that are not big data. And why is that? Basically, because there isn't a standard definition of what big data is. And I don't have one, but I do like very much one that says the big data involves data with volume, diversity, and complexity will require new techniques, algorithms, analysis, something different to be able to extract knowledge. If you can just simply do something in your laptop, that's standard machine learning. You need to do something different. And it is characterized by, well, we call it the V of big data. You may have heard of the volume, the velocity, the variety, and so forth. But basically, it means we need to do something different. When I talk about big data, I like talking about data-intensive applications. It's not only about calculations, that yes, of course, we need to make calculations, but it's more about dealing with the data, how to move the data. The new term that people are using right now is large-scale data analytics. And I could have changed the entire talk, but I don't want to. Big data sounds okay to me, all right? So that's what we are talking about here. And if you ask me, Isaac, so are you talking about 1 terabyte of data? Are you talking about petabytes of data? And I will tell you, it depends. It depends on what you have to do with that data. Sometimes even a couple of gigs of data is very challenging to deal with, and you're not going to be able to do anything with one computer. We're going to need more than one computer, and that's the bottom line of what big data actually is to me. One more aspect of big data that I wanted to highlight is, and that's why people get confused, is it has so many different phases and aspects. We might be talking about how to acquire the data, how to install the sensors in a reasonable way to then store them somewhere, and dealing with the security and privacy, how to visualize the data, and many things when we talk about it. But what I'm interested in is when you need to analyze, when you want to apply machine learning techniques, data science techniques to that. Okay, so that's what I'm going to be talking about. And now the question is, how do we deal with it? So imagine that you say, I've got there 100 terabytes of data from galaxy pictures, and I want to deal with it. And I want to do that with one computer. That basically will not work. Why? Because I doubt that you have a hard drive or even 10 hard drives in your computer to store 100 terabytes. But assume that you can actually do something like that, and you want to process that. That's going to take ages, right? So what is the solution? No rocket science here. Divide and conquer. If you're a computer scientist, you know what I'm talking about. We always solve every problem by dividing, splitting, and then conquer, finding a way to merge the results to create models that can actually learn from different pieces of data. So what I'm talking about in here is that we're going to go from what we call vertical scalability to horizontal scalability. What do I mean by that? What is vertical scalability? We call it also scale up. What does it mean? So that is when you have your data in your laptop and you're trying to deal with, to do whatever analysis you're doing, and you're like, oh dear, out of memory, out of memory, out of memory. And you have 8 gigs of data. What do you do of RAM? Sorry. What do? You go knock on the door of Emilio and say, can I get more RAM memory, please? Thank you. And he will say, okay, there you go, 200 euros, whatever, I buy more. Problem sorted. Whenever you can do that, please do that. Okay, whenever you can actually get simply pay a little bit more money and get a better computer and do your analysis, do that. But the problem is that it's going to be limited. There will be a point, you will reach a point in which you cannot upgrade your computer more and you still have a problem to deal with. Solution, obviously, using more than one computer, right? That is not rocket science, as I was saying. And what you're going to have to do is to connect all of those computers by a network. And good news about it is, do you need to have high-spec computers like, the most powerful computer? No, you don't. You simply use any computers you have lying around in your, many computing rooms that you may have here. You can just simply connect them all. And whenever you need more compute, you need more power, you simply keep adding more. Nice and simple. So what's the catch? The catch is now we're going to have something to connect them through. We need a network, and that network will be the bottleneck. And that will be what really we are struggling when designing any solution in big data, how to reduce the movement around of data through that network. And of course, that will make our software much more complex. All right. So in summary, scale up whenever you can do that, and that will solve your problem. Do so. Don't do anything else. Why? Because your software might become very, very complicated. Good news, yeah, less energy consumption. You will save a lot of money, because if you need to go scale out high performance computing, that will spend a lot of energy. You need cooling system, you need people that know how to manage that, or you need to pay cloud infrastructure to deal with it, right? So that is scale out, which is obviously the way we're gonna go in any big data. Now, what do I like about scale out? There is something I said there, fault tolerance. And what is that? What do I mean by that? Whenever you're running anything on real big data, that's gonna take a long time. That's not gonna be 5 minutes compute. But what you want is to make sure that whatever happens, if there is any hardware failure, you still get your result. You don't want to be running an experiment for 20 days, and then in the day 19th, you say, shit, now one computer crashes, and it's just basically killing the entire execution. You want something that will make your process fault tolerant. You can simply run that somewhere else, right? So many of you might be thinking, Isaac, I know what you're talking about. You're actually just simply talking about HPC, high performance computing, right? Do you know what a high performance computing cluster is? Yeah? No? Yes? Well, just in case you don't know, basically that means we've got a number of computers, all of them with their own operating system. Hopefully it's Linux, it's not a Windows machine. Yeah. Oof. All right. Yeah. So it's a Linux machine with their own hard drive, their own RAM memory. They're all connected through typically 2 different networks. One of them that is quite fast and really expensive, called InfiniBand, that we normally use just for communication across computers. And then we have a central storage where we're going to store all of our images, all the data we've got, and that's shared typically through an Ethernet network. It can be possible through InfiniBand, but really expensive. All right, so you've got that. That's what we're doing. What do you normally do with an HPC? What you normally do there is things like simulation, optimization, in which you have lots of compute, lots of calculation only. But your data is relatively small. You've got just that box in there, and that can go and be broadcast anywhere you want. And what you aim for is this 99% CPU use, right? That's what you really want. And that's why whenever you go by the HPC and the clusters that you've got there, they are running like, and the fan is like going crazy, right? That's what you want. But what happens when you want to use a traditional HPC for big data? What's going to happen is that you've got so much data and you want to have all that data available everywhere. And that's going to be, collapsing this Ethernet network. And if you know a little bit about the speed, about Ethernet and the hard drive and the RAM memory, you will know that this is super slow. Sending this block from here to here will make things slower. The more computers you add in, the more collapse will be this line, right? That's like a pipe sending data across, and that's a little bit of a problem. And that's why we cannot just simply go and say, I do big data in a traditional HPC. We need to do something else. What is that something else? The trick is on something I said very, very briefly. Here, this computer has an operating system, their own hard drive, and RAM memory. But we barely use the hard drive in here. We're using all the time this to store all the information at home. Why don't we try to store the data in a distributed way? And that's what we try to do with data-intensive job. When we have the data, the idea is to have different blocks of the data spread across the different nodes in here. And then what you do, or what you aim to do, is to simply work with the data you have locally in your computer. That sounds fantastic, but it's not always possible to do so. Some communication will happen, and you need to minimize it, right? Something you might notice if you really pay attention to it is, come on, my students, whenever they see that, they're like, oh, there are two ones, one here, one here. Come on. There are number two. What is number two again? Oh, it's here. Why do I have that? Why do you want that? Say again? Basically, what you want is, if this guy dies, I still have the data somewhere else. I can still do something with the data. Data redundancy, fault tolerance. That's what you want to build up here. And that's what we call the principle of data locality. That's what we are going to aim for whenever dealing with big data. What we want to do at the end of the day is basically apply whatever operation you want in all the data. But do you really care about where the data is? No, you don't. What you want is that the data is distributed in a way that, well, basically ensure that whenever you want to execute your operation, it will finish. You don't care at all on which node is doing what, which computer is doing what. You don't really care about that, right? You don't want to know, but you want to know that if one of them is doing something stupid, well, that task, that job that we want it to be done is done somewhere else. That's what you really want. And to do so, what we're going to look for is a way to, make an abstraction to make it simple for us so that we don't really know what's going on underneath and of the whole implementation. And the data locality is going to be crucial. It's going to be very, very important. Have you ever heard of MapReduce? MapReduce is a programming paradigm. I'm not going to describe it in detail, but if you know a little bit about programming, it's based on functional programming. And what it will allow you is to divide and conquer. The map is a way to divide your data into different splits, different chunks of data. And then what you do is to reduce, to conquer, to merge data, and to get aggregations of partial results in a way that will do your job, right? So the whole motto and idea behind MapReduce is that moving computation is going to be cheaper than moving computation and data. That used to be how we used to do things in traditional simulation, optimization techniques, and stuff like that, right? So instead of moving data together with the function that you want to apply, you simply send the function, and then the data is going to be somewhere there, right? Then we need to ensure that that works, right? And we need to ensure that actually does whatever we wanted. That is not that easy. So this is the concept. How do we use it? Luckily for us, there are people that didn't have anything better to do, and they implemented that for free, open source, and the precursor of this is Apache Hadoop. Have you ever seen this beautiful elephant before? So that guy, actually this guy, he was the inventor, the guy that came up with the idea of MapReduce. Well, he wasn't really, he was the one implementing it open source. And here are the papers that originally come from Google, actually. Hadoop is the open source implementation of this concept called MapReduce. Nowadays, that was invented a long time ago. Nowadays, we do not use Hadoop, not fully at least. They do provide an implementation of that MapReduce idea, but it's super slow. What we do use still and forever, I think, in big data is this Hadoop distributed file system. That distributed file system is the one implementing that idea of keeping the data locally and distributed across a number of computers, right? So this is why I'm talking about, because this is going to be the base of the entire big data ecosystem, we call it. But soon we found that this guy here what they were dealing with is the problem of having the data in different computers, but having the data only in a hard drive is not really efficient, because you know that to really run your program, your data needs to be in the RAM memory and not in the hard drive. If you need to load the data, that's going to take a while. And if you need to reuse your data, and you need to keep reloading the data from the drive to the main memory, that will be super slow. And that is what was exploited by one platform called Apache Spark. Have you heard of Spark before? Yeah, some people, just one person. So Apache Spark is one big data platform that is currently one of the most trending, let's say. Why? Because they do provide quite a few things, but mostly because they do provide this in-memory storage. The idea of keeping things in the main memory of the different computers. I'm going to get back to that. Something useful for you if you're a programmer is that they do provide APIs in Java, Scala, Python, and R. And nowadays, basically, all of them could work almost at the same performance. Yeah, depending on how you do it, but almost the same performance. Otherwise, you should go to Scala, which is the way it was implemented. So what did they do? What did they invent? Well, basically, they invented a way to have a distributed data structure. What is a data structure? You know what a list in Python is? So a list that rather than having their elements in one single computer, their elements are in different computers. And whenever you're programming, you simply load the data. You don't need to worry about it. You have just an object, you have a name that describes this is my data, and that data is somewhere else. You don't care about it. And that is actually the beauty of using this. It's an abstraction, basically, that allows us to do this. Initially, they implemented something called resilient distributed data sets. And now it's actually a little bit obsolete, although it's still underneath. And now they use something called data frames and data sets. If you're familiar with Python, you know data frames from the Pandas API. You can actually use those on top of Spark now. There is something called Pandas on Spark that will allow you to do everything you were doing before so much faster. Do you need a cluster? Actually, you don't. You can just simply get your Spark on your machine and use all the threads of your computer. So if you were using just a program sequentially, now you can make your program 8 times faster or 16 times faster, depending on how many cores and threads you've got in your computer, right? So far, did I lose anyone? Yeah. Yeah, you're like, what is this? What is the cosmology here? And okay. So, well, basically here is to mention, if you're a functional programmer, you might know what I mean by lazy operations. So basically, there are 2 different types of operations with this distributed data structure. And you've got this map, filter, and so forth. And then you have actions. And what happens is nothing happens until you trigger an action. And that's something that we need to get used to whenever dealing with this kind of paradigm. So what did I say so far? I was talking supposedly about machine learning, and I didn't even speak about it yet. I basically told you that there is technology down there that we need to learn how to use it. And what's the problem when you have big data and you want to do any machine learning in it? Typically, you follow the cycle. We call it the life cycle of machine learning. You want to collect your data, and that data collection will last for quite a bit of time, because you do collect some data, then you model that data. I'm going to come back to what is inside of this box. And then whenever you think is working, you deploy it, you put it to work, and then you realize that, yeah, maybe I need to re-identify what my problem actually was. I need to collect more data, and that's why it's a cycle, right? So it will be happening iteratively multiple times until we find out what we actually wanted to do. What I wanted to say here is that basically every step of the way could be really slow if you have big data. Imagine that what you have is millions of images. How can you basically even just doing an exploratory analysis, just simply checking basic statistics about the data? Imagine learning anything from it. Or imagine just simply cleaning the data. To clean the data, you need to do it in a smart way. You cannot just simply say, cleaning the data, I only take 10% of it. That's probably not a good idea, right? So you need to do it, and every step of the way could be in danger whenever dealing with big data. But it doesn't mean that whenever you have big data, every time and every step will be, or you will need to redesign it. For example, you might be able to learn something with a GPU, just your deep learning algorithm, and you learn how to classify galaxies, as I'm going to show you. And that, so that possibly for this and this, you don't need more than one computer and a GPU. That's all you need. But for example, if then you want to classify the entire universe, you're not going to be able to. But if you wanted to classify more, the deployment of that model, testing that model will take ages. And that's when you do need to distribute the computing and to do something slightly different. So you might be thinking, all right, Isaac, what you want to say here is that we need to re-implement anything we did with machine learning using the Apache Spark or whatever technology you're talking about in here, right? Just to use distributed computing. Yeah, I wish it was that easy, right? So the problem is there are many different platforms. The two I show you here, Spark and Hadoop, are two of them, but there are many of them. And depending on the problem you're dealing with, you might want to use other ones that are more aligned to the kind of processing you might be doing. For me, if you know a little bit of programming, choosing the right big data technologies, like choosing the right data structure for your problem to implement it in a fast way, right? So that's really very much the key message. And whenever doing machine learning, you need to make sure that whatever application you're doing is fault tolerant. So it will allow you to continue running even if something goes wrong in one computer or two or three computers. You will have to transform your data multiple times, because normally you don't just simply feed in raw data into a model. You need to do something with it and tweak it, and that will have to transform the data multiple times, and you probably will require multiple iterations of the data. Apache Spark actually is considering all these three aspects to do machine learning. What is the science of that? Is that purely engineering? No, you really need to think carefully how to use that kind of technology. And also the algorithms themselves. Well, maybe we need to tweak them. Maybe we need to think of a different paradigm to actually deal with big data. Many of you might be thinking, Isaac, everything is invented now in computer science. You know, you go to Python, you Google it, and you've got the scikit-learn library, you've got TensorFlow, it's got everything you want, and you're right. But not quite there yet. You're right, and many people use machine learning without knowing what is inside, and that's perfectly fine, right? We just simply take off-the-shelf technique, and we still need to know something. If you're a machine learning user, you know that you need to know a little bit about, is that model actually appropriate for the problem we have at hand? Do you understand the behavior a little bit of the technique? You know how to optimize the parameters? Do you know how to validate whatever you're doing, right? You need to know a little bit, right? And if you don't want to know anything about it, you might want to use something called AutoML, right? That is trying to make the whole process even more obscure, a little bit more dark, like a black box. You simply fill in the data, and that will decide which model is good for you, and you simply give your results. Is that possible with big data nowadays? Very challenging. That will be even more time-consuming. But do we have a platform to deal with big data and machine learning? Yes, we do. Of course, we do. And it's something called the machine learning library of Apache Spark. That is one of them. There's another one in Apache Flink and Apache Dusk as well. What do I want to say here? There are many things you can do. But the key thing is you will soon realize that the number of algorithms, the number of techniques that are currently available in that distributed nature, they're limited. You will find techniques like decision trees, like clustering, k-means. You might find SVMs. You might find linear regression, logistic regression. All that is there. Do all of them work well? Hell no. Some of them are terrible. For example, the super vector machine in that particular library, it doesn't really work. It doesn't even have kernel implementation. Why? Because doing that is super difficult in the big data context. We're still building on that. And so basically the whole thing I want to somehow tell you here is the difficulty of doing machine learning with big data, but also the possibilities. It doesn't mean that everything is impossible, right? So it is definitely possible. I'm going to share with you these slides. What I did is I put this link to Google Colab in case you're interested. I put I'm writing a book on big data at the moment for a student, and I have a full guideline on how to use the machine learning library for a particular classification problem. In case you find that interesting, you will have a full notebook in Python explaining to you step by step how to read data, how to distribute the data, how to run some basic algorithms. In case it's useful, that's for free. Please don't sell it. I want to sell it myself. Okay. Thank you. Anyway, so you might be wondering, Isaac, you did say machine learning library, you did say decision tree, you did say k-means, you mentioned a few algorithms, but what are my deep learning methods, please? I want my deep learning, because I guess many of you might be using deep learning, like everybody. Do we have this distributed deep learning? Yes, we do. Of course we do. But the thing is, in many cases, we just simply use a GPU to parallelize the processing of a deep learning method. For the average user, using one GPU, very powerful one, will be enough. For you guys, probably it's not enough, because you might have loads of data. So is it possible to distribute and do this scale out, having multiple machines, each one of them having multiple GPUs, and get all of them working, coordinate in a very nice way to do the learning of a deep neural network? Is it possible? Yes. Can you do it? Possibly we don't have the money. So the people doing anything remotely similar to it, Google, IBM, and stuff like that. Right? So this kind of company who actually have the computational power to do so. So doing research on that, for me, it's impossible. Basically, I didn't have the time nor the money to actually do any research in there. But imagining I could do, what can you do? If you have multiple computers, easy enough, you can do hyperparameter optimization of your deep learning. You can run in different computers, basically your model with these parameters, your model here with different parameters, and do that in parallel. That is super easy. You don't need any framework. You simply run it even manually if you want it, right? If you want to classify loads of data, again, following the idea of divide and conquer, you have your model, and then you deploy it in different nodes. Sorted. But here's where the cookie crumbles are. How to train a neural network in parallel. And that's the difficult thing. There are different approaches, synchronously or asynchronously, and that is going to be very, very challenging. And you might want to parallelize the data, which is exactly what I was saying before, but you can also distribute the model, because the model might be way too big to be trained in a single GPU. And for that, you follow something like this. So half of the network is trained in GPU 1, the other bit is in GPU 0, and stuff like that. Yeah, so it's really, really challenging. As I was saying, there isn't much out there. There is something open source. For example, Microsoft did Spit. There is a TensorFlow on Apache Spark that follows the same idea of I'm not sending data and code, I'm just sending the code, and then you do your thing locally, if possible. But what I found in the little reading I've been doing about it, that it's very difficult to understand what they do. There is no documentation, something that is growing, and it's something that we don't have the resources typically at universities to really deal with and to learn a lot. So the documentation is limited, but it's not impossible. If you learn about it and you want to teach me everything about it, I would be really happy to hear about it. So that's all I wanted to mention about, big data stuff, parallelization. And now I want to show you just one example of things I've been doing, which is actually not big data, but it's fine. Yeah, that was actually the closest thing I've been doing to what probably you guys doing here. And that was actually Manuel's PhD, which was all about galaxy image classification. Have you heard of citizen science? No? Yes? A few people say yes, a few people say no. So I will walk through it relatively quickly. But the idea is that if we have people that don't have anything to do at home, can we get them to do some science for us, right? And they do something. Come on, you're doing nothing. Do something. It's a form of crowdsourcing for science, right? And there have been quite a few projects pioneering by Galaxy Zoo, that is the one that we are using. And now if you go to Zoo Universe, you will find a lot of projects that are running at the minute, trying to get people, like anyone in here, actually, way too much, people that don't know anything about science, doing science. From a computer science perspective, what I like is that is a very powerful resource to do labeling at a large scale. what maybe you don't like that much is the quality of that. And that's something else I will get back to it. And this slide wasn't for you, obviously. You know what astroinformatics is, hopefully, which is the idea of combining data mining, machine learning, data science, and to your problems. One of such problems was to simply distinguish between elliptical and spiral galaxies from images, right? It's a very simple problem, and you might be, well, I have this slide not for you guys. What do we mean by morphology? Why do you want to do that? If you ask me, I will play there. You guys know way more than me about it, okay? So if you ask me, I will run away. I will say, no, I know nothing. But why do I found it actually interesting, right? So Manuel came to me when he started his PhD saying, oh, I found this cool thing called Galaxy Zoo. I have data. Why did I find it interesting? Because of the quality of data. The data that you get is complicated in many ways, right? So first thing is the hybrid types. You may have the obstacle, you may have the position. I'm going to get back to that. But more importantly is the uncertainty around the data. The data you get, the labels that you get from that project, basically users got a picture like this and they needed to say that was spiral, left, right, elliptical, or they didn't know or anything like that, or that was emergent, right? So they needed to do something like this. Why did I like the problem? From, let's say, image classification perspective, what I did like is that, well, different objects, which is this? This is elliptical, right? They have different degrees of being elliptical. How elliptical you are. It's not like there is a canonical elliptical shape, right? There are different grades. And the same thing from a spiral. You also have different angles, right? So we see the images in different angles. Okay, that is kind of sorted right now with deep learning. We can get that kind of, okay, fine, but I still found it interesting. And last but not least, there are many different things around that are not of interest. And we want to pre-process them or to do something to ignore them whenever we're learning any machine learning model. So my question was, when Manuel presented this to me, was, why on earth you want this challenging problem? You want this to that volunteers that know nothing about physics, they want to classify images. That's going to be real bad. The results that you get, they're going to be real bad. Well, some of them actually knew way too much. Some of them knew almost nothing. And what you get in the end is something like this table in here. How can we use that data? So what you got is from an ID from a galaxy, you got the number of votes, and then you got the probability of belonging to elliptical, spiral, or don't know. I'm going to get back to this data again, but what we do in citizen science in combination with machine learning is either using this data like this here and try to do something with that data. And that's what we normally call an offline approach, which is the one we followed in Manuel's PhD. Or you could follow an online approach. What is an online approach? Whenever you're running your project, you're teaching people something, right? So you're giving them things that you know is already analytical. You just want to know and score them. You want to know if they're good or not. And you want to teach them how to do it better if they don't know, right? So basically, that's the approach that we took, is the offline one. Why did we do that? Especially because there is a lack of accuracy in the results that you get from a labeling coming from citizens. And you need to deal with it. Computational intelligence and fuzzy logic specifically is actually quite suitable to deal with uncertainty. And that's what we did in our research to deal with that. And also there are different sources of uncertainty coming from things like they even said it to us, I don't know. And no one was using that before. I don't know what, but they never used it. And that's what Manuel did in his PhD. So the objective was to use and to learn how to use this data effectively. We find, obviously, the uncertainty that is, we have different classes, right? Elliptical, right-handed, left-handed spiral. You also have mergers. So that's what we call inherently uncertainty, because we may have different percentages of galaxies we find in the different places, right? So mergers, I guess there are less mergers than normal galaxies. right? For example, and learning in that scenario, it might be really difficult. There's some measure uncertainty. What does it mean? They told us if they knew it or not. On this decade, don't know, and no one used it. Can we use it? Can we exploit that information? And also, we have the number of people that voted for that particular galaxy, right? If we had for a particular galaxy only 2 votes, can you trust that particular labeling? Can you not? So what we did in Manuel's PhD was initially to use a fuzzy-ish based approach to handle and to modify that data in a way that was taking into consideration of all of those sources of uncertainty. Whenever we did that, at the very end, we were using actually expert label data and a subset of the entire galaxy to catalog, to refine and to check that what we were doing actually made a little bit of sense. Obviously, it doesn't mean that experts are perfect, and they might be actually wrong. We found a few mistakes that didn't make any sense. But apart from that, we took it as our ground truth, right? So we had 41,000 expert classifications within the subset, within the set of 600,000 classifications that we have from galaxies, right? So we used that, and we came up with this approach to handle uncertainty. And if you want to have a look at the paper, you will see all the details on those very fancy mathematical transformations. They're actually abbreviated and no more than that, but they look good and they work. So what did we do after that? That's not machine learning, not even deep learning. What we did is, now that we have the data in a shape that it makes sense, now we feed that into the deep learning model. In the first approach that was presented in this paper in 2020, the first thing that we did is, what is going to be better here? To use standard machine learning, like decision trees, simple vector machines, and stuff like that, using some feature extractors that were well known in the field, or we should use deep learning that is more of a black box. We don't really understand what's going on to transform the images into something else. And we compared that, and we applied different techniques, and we found out that using deep learning obviously was actually a little bit better. And after that, we were like, okay, so here we have something very interesting. We call the amateur classifications, right? But they do have some uncertainty. We have somehow mitigated. We have the experts that gave us a subset of classification. And then we have plenty of data that is fully unlabeled. So we were wondering, is there a way to use all of it at once? To learn a model that uses the 3 things: unlabeled data, data coming from amateurs, data coming from experts, right? And use it all in an integrated framework. And that's what we wanted to do. If you're familiar with semi-supervised learning, this is very much the same, but rather than having unlabeled and labeled, you have unlabeled, labels better, right? And they come in different subsets. So we came up with a solution that I'm not going to really detail completely, but basically we use all the unlabeled data using an open encoder method that was used to pre-train what we're going to be doing at the very, very end. And that's the way you use the unlabeled data. Then every instance, every galaxy that we have with amateur label, we use that to keep pre-training our network. So we move a few layers from here down to the second stage of the method. We kept learning. And then after that, we were using the classifications from the experts, but also using those that we really trust from our model, original model, in which we handle the uncertainty. So we came up with a way to somehow find the correlation between what normally amateurs say and what normally experts say. We found that correlation, and we used a simple NLP there to put it in and have what we call enhanced amateur labels. And that was the last stage of the method, this fine-tuning process in the end of the whole framework. Simple, quite effective actually. Here are some results, and not even presenting the whole thing because we did the binary classification problem, which is, elliptical versus spiral, but we also have right and left elliptical, and we also have merger versus anything else. right? So we did all of them, and here you see some results. And what you see is that using more data, obviously, will give you better results. In the binary case, actually, we get very close to what we call the oracles. The oracles were just actually learning from experts. What can we get? 95%, actually quite accurate, I would say. We got real close to it, 94. These are different variations of our method, but the same kind of idea in most cases. This one didn't use a label, if I remember correctly, and this one is using a label as well. But whenever the problem was more complicated, like in a multi-class classification problem here, we have 3 different classes. Well, things became a bit more difficult, and we got even, well, quite decent 71%, but it's still far from the oracle. So that means that probably we still have somewhere to do in this field. And I think I'm running out of time, so I'm not gonna really go into the next problem that I had, but I will share with you the slides in case you want to have a look. The bottom line of what I wanted to show here is that sometimes you've got models, you learn a machine learning model, whichever that is, and then you have new data, and then you need to update your model. And that, when you have big data, it will take time. And you need to think carefully how to model that to keep learning and learn how to forget and learn how to get what is actually happening now. Is that going to happen in the universe? I don't think the universe is evolving so fast, but there might be things in which you guys can use this idea. But also what we did basically is a data summarization visualization technique. So basically we have lots of data from incidents in the UK, and what we were trying to find is something that visually you can actually tell someone, hey, watch out, this is a hot spot, right? So that's what we wanted to do, and basically what we did is from this amount of data, reducing it, and then learning how to keep those subsets that were of interest, well, during the whole time, right? So this is actually being used in England at the minute by, well, basically 30% of the fleet of the UK. So couriers like DHL or Sainsbury's, if you know the supermarket, or Tesco, all of those drivers, they do get, whenever they go from point A to point B, they know what the hotspots in that flow is, and sometimes they use it to plan better where they're going. And the hotspot could be for many things. Could be here you might be speeding, here you might need to brake harshly or anything like that. Yeah. So I'm not going to detail this, and I'm going to move basically to the conclusions, in which, well, here are all the slides. And this is basically the whole approach. You go step by step from an initial big data set. You apply our method to reduce the set, and then after that, we keep that as the input to the next method and keep updating the base of knowledge, let's say, right? So I'm going to try to go a bit more quickly here and just basically say goodbye. Because I think, yep, it's already quite long, and you're still awake, I think, or you want to have lunch. So, well, in conclusion, what I wanted to, the message I wanted to convey in here is that whenever we have big data, large scale data analytics, anywhere you mean, it doesn't matter. It means you need distributed computing. It means you need more than one computer. Doing so is not straightforward. We really need to think carefully how to do it. For a few things already, we have quite well-established methodologies. So maybe for many of the problems you may have, I can solve that in 2 minutes. Okay, go there, download this, run it. For many other things, I might need to think very carefully how to do it, right? You need to be creative whenever you have something that is not traditional. For example, that learning from unlabeled data that was labeled but you couldn't track, and maybe experts data, using all of that kind of knowledge in a smart way. Sometimes you need to come up with your own solution. That's what we did in there. And the use of fuzzy logic, the use of computational intelligence techniques, they really help quite a bit whenever we're dealing with uncertainty in your data. Many people right now are working on explainable AI, if you heard of that, yeah, which is trying to make sense of AI. So basically, sometimes we've got the model saying, oh, that's an elliptical galaxy. Why do you think that? And now you're trying to get even natural language telling you, I think this is an elliptical because I see this and this and this. right? And that's what they want to get right now. And that's where we are heading as well. So that's all I wanted to mention. Thank you very much for listening. I like this one more than the Nottingham one. So that was it. Thank you very much. Any questions?
Thank you very much, Isaac, for this wonderful talk. I have several questions, but maybe Francisco can start with the questions on the room.
Yeah, and just tell me if there is someone in Zoom with questions. So question in the room? Go ahead.
Really one question, and after that, some random. First question. The question is: do you know that Spark, Apache Spark we can use GPUs?
Yeah, they can. Yeah.
So if you don't use the extra tools, you can use the algorithm that we are using in Spark directly in GPU.
How good is that?
Okay. It's not a traditional C code to run.
Yeah.
And second, it's about a practical point of view to use Spark tool on large database. In that sense, you need a computation cluster to run these tools. This means that you need a people that can install the software tools and mount it. After that, the data must be in a polarized form. That's in our work. It's we have to compete. The fixed file. It's the data format. There is a preliminary parallelization of its from SSL people. But if you don't have this parallelization of the format, you can use Spark, Hadoop, or anything. And the third random thinking is that Spark is written in Scala. It's a functional programming. So you can use Python or Java, okay, but only if your algorithm is very simple. In our case, you have a crazy syntax because Python and Java are not.
I disagree a little bit with you in there because Python is actually quite functional as well. And you do have this very same thing with map and reviews and anything you want. The only thing that is slightly different from Scala and Python in there, I mean, I do love Scala, by the way, it's my favorite language today. But the only thing that used to be a problem was performance. Because in Python, you're working in Python, and that is later translated to Java. And there was a double serialization, changing from one data type, the language, then to another one. But with the latest API, they came up with the data frame and the data set. That actually happened automatically, and it's the same efficiency in any language because everything goes to Java in the end. And there is an engine underneath Spark that will do all that automatically for you. So nowadays, I mean, it depends on what you want to do. From my point of view, if you just simply want to use Spark, just simply get your data, analyze it, run some algorithms, you can do it in the language you want. But if you're designing a new algorithm for Spark, like designing, then you need to go to Scala because you want the performance and because you want that to be well integrated. Sure, yeah, I would say yeah. Everything I've done in my research is Scala. Everything I do in my teaching is Python for the student. But it depends.
Yeah, we can talk
Sure.
about the syntax. So we're using Spark from Python or from Java. In my opinion, the only way to create a complex algorithm is in Scala. Okay, in my phone.
Could be, yeah. If you want to really design something like pieces within an algorithm, I agree. You need to do it in Scala, but more for efficiency reasons than, I mean, visually or the writing. But I think that's a matter of preference, really, in my opinion. Thank you. More questions?
More questions? Rene, there are questions in Zoom?
I do not see here, but if they allow me, I want to make a comment. Yes, here at the Institute, we have a small cluster with Hadoop and Scala, and the person that is responsible for this is the one that asked you the first question, Rafael. So thank you, Rafael. And we are applying this small cluster for solving 20 years of CCD images of asteroids and extracting all the information that we have on that images for the asteroids. So there is a lot of development of a new algorithm for extracting all the physical properties from the images. So yes, we are doing this kind of computing that you explained, and I am really happy that we can find another person that share the same interest here. So we need to talk after your talk.
Sounds good. Sounds promising.
Okay, there's another question.
Thank you very much for this nice talk and very interesting. So my question is particular for you is, are you now working in a particular nation problem or?
I'm working in many different things at the same time as a good computer scientist. So I'm parallelizing my research. But what I do, depending on who I'm working with,
I consider that you can tell us what kind of application to science is already.
let's see how much I can say. So, for example, with the work I do with Unilever, I cannot tell you much more than, we're making ice creams. I'm looking at the freezers and data from those sensors. And the point, obviously, is to make them make money. But that's all I can tell you, and to make their businesses more, that's the open. I'm looking at the public definition we have of the project that says something like we are designing big data tool to make their business processes more efficient. Basically, what we do is optimizing the processes by applying machine learning to predict something and use those predictions to then optimize how they do things, right? An example I could give you that we did a few years back that has nothing to do with physics, by the way, was with Subway. Well, that was the end user was Subway. And what they had is many people that actually work just a few hours. So they don't work like full-time 9 to 5. Coming up with a timetable of who is working at what time is a challenging problem, right? Because they don't know. So using a lot of data coming from directly from the counter, right? So transactions data and a few more things about events happening in the surroundings, location, and stuff like that. We came up with machine learning plus optimization technique. The machine learning was trying to learn how managers were doing that kind of timetable. And then we predicted what the manager would do in that situation for the coming week. Then we gave them a schedule. And that schedule was optimized to basically save money, right? And put just enough people to be able to cope with the demand. Initially, we did it without machine learning, meaning we were just optimizing and getting the best schedule. Whenever we gave that to them, they were like, no. AI, they don't know nothing. But if you give them something that it looks very much like what they would do, and that we did with machine learning how they normally do it, they were amused. They were like, oh, that's exactly what I would do. Why do you do this? Okay. And now we're saving 200 euros this week. And so that's the kind of, we call it predict and optimize. But I don't think that will apply a lot in your field. I think maybe, but I don't see it straightforwardly. I think more any prediction type thing is what it really applies to you. Predicting what's going to happen, or classifying, or segmenting. We did a lot of segmentation of customers to understand and find anomalies as well. And that kind of thing, yes, I find it probably way more aligned to what you do.
Okay, thank you.
Okay, now some other questions in Zoom connect.
Not here, no.
Okay, so let's then thank Zach again for
Thank you.
talk.